Hello, this is Rick from MathX, and today I'd like to go through another set of concepts, Euler's Totient theorem and Fermat's little theorem. Now, these theorems are useful to know in number theory, and they can help you solve a lot of problems. However, they're a little hard to grasp, so that's why I'll be going over them today, to teach you these slightly confusing but useful theorems. Now, before we go into these theorems, there's something you need to be familiar with, and this is called modulus. Modulus is basically a way of notating numbers as the remainder of other numbers. Now, what does this mean? Let's say we have one number, like 49, and we want to find out what 49 mod 5 is. To do that, we would think about what would we get as a remainder when we divide 49 by 5. Well, the smallest multiple of 5 less than 49 is 45, and 45 plus 4 is 49. So thus, the remainder we receive when 49 is taken mod 5, we get 4 mod 5. And we write this out by using 3 lines, because we're not doing equals. We're denoting that these are congruent with one another, which basically means these are the same thing. 49 mod 5 is the same thing as 4 mod 5. Because the idea is that the remainder, when we divide either of these two by 5, is going to be 4. Now we can also express this by something else. Instead of looking at the largest multiple of 5 less than 49, we can search for the smallest multiple of 5 greater than 49. Now, the smallest multiple of 5 greater than 49 is 50. And this is 1 less than 50. So we can also express 4 mod 5 and 49 mod 5 as being congruent to negative 1 mod 5, because it's 1 less than a multiple of 5. So that's basically how modulus works. We just divide the number outside the modulus to find the remainder, and we express that as the remainder mod the number itself. And we can do the same thing except with negative numbers. To make sure you get the concept, I'll be trying out with some other numbers. So let's try to find out what 23 mod 7 is, 36 mod 8 is, and then what 17 mod 4 is. So you can try these problems on your own, and then after you finish these problems, I'll review the answers with you. Okay, so by now you've probably attempted all of these problems. So let's go over them. So if we want to find 23 mod 7, let's think about this. What's the largest multiple of 7 less than 23? Well, the largest multiple of 7 less than 23 is 21. Now 23 minus 21 will give us a remainder of 2. So since we get a remainder of 2, we can write this as 2 mod 7. If we want to write this as negative numbers, what's the smallest multiple of 7 greater than 23? That's 28. 28 is exactly 5 more than 23. So we can express 23 as negative 5 mod 7. 5 less than a multiple of 7. Now, there's a cool pattern we can find here, okay? When we find something in terms of positive mod 7 and negative mod 7, if we make this negative positive and add these two up, we're going to get 5. And the same thing is going to happen when we do the same thing to 2 and 5. If we negate negative 5 again, we're going to get 5, and 5 plus 2 is 7. And this makes sense, because this number, this mod, tells us the distance, whatever this value is, from a multiple of 7. It's 2 more than a smaller multiple of 7, but 5 less than a larger multiple of 7. And these two numbers would add up to 7 because multiples of 7 are within 7 of each other. Anyways, now on to the next problem. If we want to find 36 mod 8, we need to find the remainder when 36 is divided by 8. So the largest multiple of 8 less than 36 is 32, and 32 is exactly 4 less than 36. So we can express it as 4 mod 8. Now, if we look the other way, we want to express it as a negative number mod 8. Well, let's see. The smallest multiple of 8 greater than 36 is 40, and that's exactly 4 more than 36. So, to get 36, we have to go negative 4. So it would be negative 4 mod 8. Finally, we're on the last one here, 17 mod 4. So, the largest multiple of 4 less than 17 is 16, and 17 is exactly 1 more than that. So we can express 17 mod 4 as 1 mod 4. Now if we look the other way, the smallest multiple of 4 greater than 17 is 20, and it's exactly 3 more than 17. So in order to get 17 from 20, we have to subtract 3. So we get negative 3 mod 4. So here's just some simple modulus practice. And now, hopefully by this point you understand how modulus works. We just take the remainder of when we divide the number outside the modulus from the number inside the modulus. And we just express that mod the number. So we use this tool to express larger numbers in terms of smaller numbers. And this is where we can start applying our theorems onto this. So I'm first going to start with Euler's Totient theorem. Euler's Totient theorem states that for any two numbers a and m, where a and m are relatively prime, a to the power of the totient of m is congruent to 1 mod m. Now what does this mean? I brought up this weird totient symbol that I haven't talked about before. Basically, the totient is something you do to a number. Here's how you find the totient of any number. Let's find the totient of a number like 15. So the first step into finding the totient of a number is to break it up into its prime factors. So in the case of 15, it's 3 and 5. Now, once we get its prime factors, then we write them out as fractions, with 3 being on the denominator and a number 1 less than 3 on the numerator. So a number 1 less than 3 is 2/3. We do the same thing with 5. We keep 5 in the denominator, and we put a number 1 less than 5 in the numerator, so 4. And then we multiply that by 15. 15 times 2/3 is 10, and then 10 times 4/5 will give us 8. So the totient of 15 is 8. Now what if, instead of 15, we got 45, and that was 3 squared? How would we find the totient of that? Well, we don't really care about exponents when finding the totient functions. Once again, we would do the exact same steps as we did with 15. We would bring down the 3, and we would write it as 3 with the number 1 less than 3 on the numerator. Do the same thing with 5. We'd bring down 5 and write a number 1 less than 5 on the numerator. And then we'd multiply these two with 45 to get our totient of 45. 45 times 2/3 would give us 30, and then 30, 4/5 of 30 would give us 24. So the totient of 45 is 24. So with that being said, I'm going to write out a couple more totient and you can practice finding them yourself. So question 1 will be find the totient of 80. Next one will be find totient of 24. I'm going to end it with find the totient of 60. So find these on your own, and then I'll come back to you with the answers to these problems. So hopefully you found the totient of them on your own. So now to review the answers. Now the first step into finding these totient is to break it up into its prime factorizations. So 80 can be written as 2 to the 4th times 5. When we write this as a number with 2 minus 1 over on the numerator and then 2 on the denominator, we would get 1/2. And if we do the same thing to 5, we get 5 on the denominator and a number 1 less than 5 on the numerator, we get 4/5. And now the final step would just be to multiply this by 80. So doing that, we get 80 times 4/5, which would give us 64, and then 64 times 1/2, which would give us 32. So we can see that the totient of 80 is equal to 32. Next one, we break up 24 into its prime factors. 2 cubed times 3. Once again, we rewrite this as a number 1 less than 2 over 2 and a number 1 less than 3 over 3. So 2 minus 1 is 1 and then over 2, so it's 1/2. And then 3 minus 1 is 2 and then we write that over 3. So we get 2/3. And then we just finally have to multiply that by 24. So then we can quickly compute this. So 24 times 2/3 would give us 16, and then 16 times 1/2 would give us 8. Totient of 24 is 8. Now finally, we need to find the totient of 36. So the prime factorization of 36 can be written as 2 squared times 3 squared. Now we do the same thing as before. 1 less than 2 over 2 and 1 less than 3 over 3. So we'll get 1/2 and 2/3 again. Then our final step is to multiply this by 36. 2/3 times 36 will give us 24. 24 times 1/2 would give us 12. So the totient of 36 is 12. So as you can see, this is how you find the totient of different numbers. Well, this basically shows us an interesting thing. If we have two numbers relatively prime to each other, let's take m to be 36 and then a to be 7. 7 and 36 are relatively prime with each other. They have no common factor except for 1. So that means that 7 to the power of the totient of 36 would be congruent to 1 mod 36. And this kind of property would be really useful if we try to find the remainder when a larger number is put mod 36. Anyways, I'll show examples of said kinds of questions later. So let's try something else. Let's say m is a prime number. Then what would happen? So let's just try the totient function, but if m was a prime number. So I'm going to rewrite it down here, or I'm just going to copy and paste it, and we'll see what happens when m is a prime number. How will the Euler's Totient theorem work then? So if m is a prime number, let's say m is 7, because 7 is a good example of a prime number. Then to find the totient of m, we would find the prime factorization of 7. Now the prime factorization of 7 is just 7. We can't do anything else to it. So if we express this as 1 less than 7 over 7, we would get 6 sevens. And then multiplying that by 7, we'd get 7 times 6 over 7, which is just 6. So we see that if a and m are relatively prime, a to the 6 would be congruent to 1 mod 7. That's kind of cool because 6 is 1 less than 7. What about if what if m was another prime number? Now let's say m was 13. The prime factorization of 13 once again is just 13. So then if we do the same thing we've been doing before, express it as now the number 1 less than 13 over 13, we get 12 over 13. And then the final step to find the totient of that is to multiply that by 13. We're doing that, we get 12. So we see an interesting new identity. If m is prime and a is relatively prime to m, then a to the power of m minus 1 is congruent to 1 mod m. Now, This is just a more specific example of Euler's Totient theorem, where M is prime, but this is also known as Fermat's little theorem. And this theorem goes as I've said before. If M is prime and A is relatively prime to M, A to the power of M minus 1 is congruent to 1 mod M. So using Euler's Totient theorem I've discussed here, where M and A are relatively prime and A to the power of the totient of M is congruent to 1 mod M, we do the same kind of thing here. And the only reason it works is because the totient of M is always just M minus 1. So this was Euler's Totient theorem, a broader case, and then here's Fermat's little theorem. If there's one if you can only remember one though, you should probably remember Euler's Totient theorem. Because just applying Euler's Totient theorem, where M is prime, we're going to get Fermat's little theorem. So we see that Euler's Totient theorem and Fermat's little theorem are both connected with one another. So let's do some practice problems applying either Euler's Totient theorem or Fermat's little theorem. So here they are, my 4 practice problems. What is 2 to the 1000 mod 13? What are the last 2 digits of 37 to the 800? What is 3 to the 2012 mod 17? And what are the last 2 digits of 2002? So take a minute to try these problems by yourself. Then once you have answers, come back and we'll discuss the solutions. So hopefully by now you have answers for these problems. So let's go over the solutions. Now, looking at this problem, we see that we're trying to find the mod of a prime number. So which of the theorems did we use involves prime numbers? Fermat's little theorem. Fermat's little theorem tells us that if M is prime, then A to the power M minus 1 is 1 mod M. So that tells us that in this case A is R2, relatively prime to the 13. 2 to the power of 13 minus 1, which is 12, is going to be congruent to 1 mod 13. So we know for every 2 to the 12th, we're going to get 1 mod 13. So 2 to the 12th is going to be 1 mod 13. 2 to the 24th is just 2 to the 12th times 2 to the 12th. So 1 mod 13 times 1 mod 13, which will give us 1 mod 13 again. So we just try to find out what the remainder is when 1000 is divided by 12. So when we divide 1000 from a 12, we will get 83, with the closest multiple of 12 to 1000 being 996. So that tells us that after we do all our 1 mod 13s, we're going to be left with 4 2's left. So 2 to the 4, which we have to take mod 13. Because all the other ones will just result to 1 mod 13. We're just going to have to deal with the 2 to the 4. So what is 2 to the 4 mod 13? Well, 2 to the 4 is 16. And if we take 16 mod 13, well, 16 is only 3 more than a multiple of 13. So we get 16 to be 3 mod 13. So 2 to the 4 is 3 mod 13. So ultimately we get that as our answer. 2 to the 1000 mod 13 is just 3 mod 13. So review 1 is just done. Review 2, the last 2 digits of 37 to the 800. Now, we don't have a theorem that deals with the last 2 digits. However, it's important to note that taking anything mod 100 will give us the last 2 digits. So essentially the problem comes down to, what is 37 to the 800 mod 100? Now, which of the theorems that we talk about involve non-prime numbers? Fermat's little theorem only deals with when M is prime, but Euler's Totient theorem deals with M when it's not prime. So we use Euler's Totient theorem to figure out what's the largest power of 37, which is congruent to 1 mod 100. So the first step into using Euler's Totient theorem is to find the totient of 100. Now the prime factorization of 100 is 2 squared times 5 squared. So if we do our next steps into finding the totient, we express this as the number under the number minus 1. So 2 minus 1 over 2, which is 1/2, and then 5 minus 1 over 5, which is 4/5, and then we multiply that by 100. Now 100 times 1/2 would give us 50, and then 50 times 4/5 would give us 40. So we know that the totient of 100 is 40. Now that means that if A and M are relatively prime, A to the power of 40 will be congruent to 1 mod 100. Now 37 and 100 are relatively prime. They share no other common factors except for 1. So 37 to the 40 will be congruent to 1 mod 100. So every 37 to the 40 is 1 mod 100. So if we do this 20 times, we're going to get 37 to the 800. And if we raise 1 to the 20 times, we're going to get 1 mod 100 still. Because 1 to the power of anything, any integer value will give us 1. So since if we just raise these both to the 20th power, we're going to get 37 to the 800. We're going to get that is going to be congruent to 1 mod 100. Thus, the last two digits of 37 to the 800 will just be 1. So that's our answer for challenge 2. Challenge 3. 3 to the 2012 mod 17. Now, once again, we're dealing with a mod that's a prime number. If we have a prime number, we're using Fermat's little theorem. So Fermat's little theorem will say that A to the m minus 1 is congruent to 1 mod m. So 3 to the 17 minus 1, which is 16, is congruent to 1 mod 17. Now we just need to find out what the remainder is when 2012 is divided by 16. Well, the closest multiple of 16 to 2012 is 2000. So that means that if we repeat this 125 times, we're going to get that 3 to the 2000 is congruent to 1 mod 17. But then we're still left with finding whatever 3 to the 12th is, mod 17. Now, that isn't some easy calculation, because 3 to the 12th will be a pretty big number. However, if we do something slightly different, if we go to the smallest multiple of 16 greater than 2012, we get 3 to the 2016 also be congruent to 1 mod 17. Now, this is useful to know because in order to get from 3 to the 2016 to 3 to the 12th, we need to divide 3 to the 2016th by 3 to the 4th, or 81. And 81, well, that's congruent to 13 mod 17 or negative 4 mod 17. Now, what number would multiply with negative 4 to get 1 mod 17? Well, 4 times negative 4 will give us negative 16, which is 1 more than a multiple of 17, telling us if we divide this, we're going to be left with 4 mod 17. So if we divide the right side, we're going to be left with 4 mod 17. But if we divide the left side, we're going to be left with 3 to the 2012. So we get 3 to the 2012 is congruent to 4 mod 17. So we did the third challenge problem. Finally, our final challenge problem, the last two digits of 2 to the 202. So as I've said before, in order to find the last two digits of a number, we need to take that number mod 100. So we have to write this as 2 to the 2002 mod 100. Now, this is where it gets interesting, because although at first glance you may be tempted to use Euler's Totient theorem, remember that only works when A and M are relatively prime. In this case, 2 and 100 are not relatively prime with one another. So you gotta think a little harder. Well, 100 is just a product of 4 and 25. So if we find out what 2 to the 2002 is in terms of mod 25 and mod 4, we can find it out what it is mod 100. Well, 2 to the 2002 is 0 mod 4, because 2 to the 2 is 0 mod 4, and 2 to the 2002 is just 2 to the 2 raised to the 1001. So we already know that this thing is 0 mod 4. But as for 2 to the 2002 mod 25, well, we're going to have to use Euler's Totient theorem there. So 2 to the 2002 mod 25, if we find the totient of 25, we need to find the prime factorization. So 25 is equal to 5 squared. So it just comes down to 4/5 times 25, which gives us 20. So we know that 2 to the 20th is congruent to 1 mod 25. So that means for every 2 to the 20th, we're going to be left with 1 mod 25. So if we take the remainder of when 2002 is divided by 20, we're going to be left with 2 to the 2, which we have to take mod 25. Now, that's just 4, so it's going to be the same as 4 mod 25. So now we need to find a number that is 4 mod 25 and 0 mod 4 at the same time. So we use some basic Chinese remainder theorem, which is bashing. So 4 mod 25, well, it could be 25 times 0 plus 4, which would give us 4, which is also 0 mod 4. But are there any other numbers that work? Well, 25 times 1 plus 4 would give us 29, which is not 0 mod 4. 25 times 2 would give us 50 plus 4, which is 54, also not multiple of 4. And then 25 times 3 would give us 75 plus 4, which is 79, also not multiple of 4. So then we see that the only way this would work, is if the last digit is 4. So then the last two digits would be 0, 4. So here we've worked through several problems using Fermat's little theorem and Euler's Totient theorems. Two very essential theorems to do well in number theory. And these two theorems are related to each other, as Fermat's little theorem is just a application of Euler's Totient theorem to a prime number. So if you get really good with these Totient theorems, number theory problems should not give you any difficulty at all. And you should be able to find out what any number mod another number is, and the last two digits of whole numbers. So continue learning about number theory, and continue applying Euler's Totient theorem and Fermat's little theorem, and become the master at these kinds of problems.